Okay, so today we're going to be looking at Euler's number. So Euler's number is an irrational number, just like pi. We write it as e, and it's approximately equal to 2.71828182845 and continues on. So it's named after Leonard Euler, a famous mathematician, but was actually discovered by Bernoulli. So where is Euler's number used? Well, we call it the growth constant. It's the base rate for exponential growth and decay. It's used a lot in compound interest. We have a formula for in financial math that is A equals P e to the RT, where E is that Euler's number. It's also found all the time in natural growth and decay. And I just want to mention too, it's related to ln x. So ln is ln. It is the natural logarithm. So we want to figure out, because we're in calculus class, this is all about derivatives, what is the derivative of e to the x? So I found a great graph online that has the e to the x, is that exponential curve that you can see there, and I also have three slopes for the equation. So let's just kind of fill out a chart here and discover kind of a relationship between e to the x and the derivative of e to the x. So we'll start with the easy case where x is equal to 0. We know when x is equal to 0, y is equal to 1. That's what anything to the power of 0 is. But take a look at that slope. So if we follow the line, the tangent line at 0, 1, we can see it actually has a slope of 1. So the y value is 1 and my slope is 1. So it's going to come over to my chart and I'm going to fill out that when x is 0, y is 1, and the derivative or the slope of the tangent is also 1. Let's check out a couple more points here. So when x is equal to 1, we know what e is equal to. It's 2.7. And looking at my graph, it's 2.72 because we just rounded up 2.71828. So 2.72. So the y value is 2.72. And if we follow that tangent line up, the slope is also 2.72. And let's just look at the last point to see if this continues. So when x is equal to 2, we'd be able to find out that our y value would be 7.39. So e to the 2 is 7.39. And if we follow that tangent line down, the slope is 7.39. So what does this tell us? And does this work for all points? Well, if we look at my Desmos thing I've got set up here, we can see in the graph here that d of a is the derivative at point A. And then on my graph, you can see the y value. So as I play around and move this a value, you can see that my derivative and my y value is the same. So again, if I could put that at right at 0, which is hard to do on this touchscreen, we would see that we get a point of 1. But anywhere we go, we can see that the derivative at point A, so d of a, is 9.9741, blah, blah, blah. And my y value, looking at the graph, is the exact same. So everywhere on the graph of e at x, the derivative is equal to the y value. Okay, so what did we learn? We learned that the derivative of e at x is e of x. So to write it a little bit more formally, if f at x is equal to e at x, then f prime at x is equal to e at x. So this is going to be the easiest derivative to find because the derivative is the formula. If we have e to the power of something, so e to the power of g at x, then the derivative is just the derivative of the exponent times the original function. It's kind of like we're using a chain law. We take the derivative of e at x, which is just e at x, or e of g at x is g at x, and we just times it by the derivative of kind of the inner function, so g prime at x. So this is very much related to the chain rule, as most of the things we see will be really just a chain rule. So let's figure out how to do this then. So if f at x equals e to the power of g at x, then f prime at x equals g prime at x times e to the g at x. Okay, and it doesn't matter which way we write these in. It's just a little bit mathematically nicer when we put constants in front of our function. But if you think of the chain rule, we take the derivative of our e at x. In this case, it's still going to be e to the 5x. And then we times that by the derivative of the inner function, which is 5x. So the derivative of 5x is 5. And then again, just to write that down a little bit nicer, we write it down as 5e to the 5x. Okay, let's look at another example here. So if we have y equals e to the power of x plus 1, we are going to find our derivative by taking the derivative of the exponent and multiplying it by the original function. So the derivative of x plus 1 is 1. And then we're timesing that by e to the x plus 1. So this is another case where the derivative is the same as a function, because the derivative of my exponent is 1. So we'll kind of step it up here. We'll try to find some more derivatives. So this case here, we have e to the power of x cubed. So it doesn't matter where we do things. Just to make it kind of look nicer, I'm going to get in the habit of writing the derivative of my exponent first and then rewriting my original function. Because if you remember what it says up here is that f prime at x equals g prime at x. So you can see that's the derivative of the exponent. And then we're just timesing it by the original function again. So chain rule is really what we're using here. And we usually say times it by the derivative at the end, but it's just nicer. It's going to turn out kind of a little bit nicer if we just times it by the derivative of the exponent first and then rewrite our equation down. So what is the derivative of x cubed? Well, that's going to be 3x squared. Then we're going to times that again by our original function. So we can make these like a little bit crazier with the exponent, but it's still going to be the same thing. We may need to include some brackets. So my derivative equals the derivative of the exponent. So I can just use power rule a couple of times here, technically 3 times. So the derivative of 2x to the power of 5 is going to be 10x to the power of 4. The derivative of 4x is 4. The derivative of negative 1 is 0, so I'm not going to write that down. And then I just come along and I write down my original function again. That's what we discovered there, that the derivative of e to the power of anything is e to the power of anything. So just using the chain rule, we just have to, again, multiply that by the derivative of the exponent. So we can see that we could have these in combination of any other of the derivative laws that we saw. So here's an example using a product rule, but it's going to be kind of the same thing, just break it down. So my product rule says f prime times g plus f g prime. So let me just write that off to the side here. So the product rule is saying I need to do like f g prime plus, f prime g plus f g prime. So there is my derivative. That's my product rule that I'm going to use. Kind of as a shorthand notation. I'm not writing down all the f at x. It's just f prime g plus f g prime. So looking at this equation here, I have to find the derivative of x squared, which is 2x. Then I just rewrite my g, which is e to the x. then I put a plus in there, and then I leave f as is, so x squared, and then I times it by g prime, so the derivative of e to the x is e to the x. And if you think about this again, we're really timesing this by the derivative of the exponent every time, but what's the derivative of x? It's just 1. So it's not really a different rule. We're always just timesing it by the derivative of the exponent times the original function. But in this case, again, the derivative of x is 1, so I don't need to write it down. And I could make this look a little bit nicer. Like I could see that I could take out probably an x e to the x, and I could be left with 2 plus x. So I can write it kind of nicely. Factored form is probably our best way to do this, and we'll see why when we get into optimization. So let's look at the next one here. So now we've got Euler's number, or the function e to the x, inside a radical. I don't like trying to do the derivative of the radical kind of just off the top of my head. So the first step I always like to do is kind of rewrite things. So I can rewrite that as a fractional exponent. So that's the first thing I like to do, just to help me visualize it. Now I am able to take the derivative a little bit easier. So remember chain rule, we're going to bring it down, kind of treat it like a power rule. We're going to bring that 1/3 down. Then we're going to leave the bracket as is. Then we subtract 1. And then we times it by the derivative of what's inside. So the derivative of x is 1. The derivative of e to the x is e to the x. Now I could just write this in a little bit nicer form. There's nothing to common factor out here. It's already kind of in a factored form. So I don't want to kind of like expand anything here. If I'm expanding a single term in, sometimes I'll do that, but never a binomial times a binomial, let alone the fact that I've got a negative exponent. So really all I want to do is get rid of that negative exponent. So I'm going to be left with 1 minus e to the x over 3. And then we can write this back in a radical form if we want, or we could just leave it as a positive exponent once I move it to the denominator. Okay, so now we've seen e to the x used in a couple different situations. We'll go back to another exercise here, and you're going to see this happening over and over again because it's one of the most common problems we do. It's find the equation of the tangent to the function y equals e to the x plus 3x over e to the 2x at x equals 0. So if I want to find an equation, I need to find a slope. Well, what is a derivative? The derivative is the slope. So some of you haven't been doing enough practice to have that memorized yet, that the derivative and slope are the same thing. So if I can find my derivative and then substitute x equals 0, I'm going to get the exact slope I need. So the first step, and almost every time in calculus, the first step is going to be finding the derivative. Now, sometimes we like to simplify our equation. And you could, some of you do prefer product rule, so you could move that e to the 2x up and make the exponent negative, but I am just going to do the quotient rule for practice. So the quotient rule, I'm going to write it off to the side here. The quotient rule says I should do f prime g minus f g prime over g squared. Oops. Sorry, got ahead of myself there. G squared. So you can see again, it's almost the same as the product rule, except for we have a subtraction in between and we have to put it over the denominator squared. You'll see that again. If you do make this into a product rule, you will get the exact same thing. But we're going to, again, use the quotient rule. So my f, or my y prime, or f at x prime, dy by dx, remember they all mean the same thing, is going to be derivative of the top. So if I just do this step by step, so the derivative of the top, so the derivative of e to the x is e to the x. The derivative of plus 3x is plus 3. Now I'm going to leave my denominator the same, so e to the 2x. minus, oh, better erase my equation over here, give me some space, minus, so I'm going to leave the top the same, times the derivative of the bottom. So I'm going to do the looking at the denominator, I'm going to look at e to the 2x. So then I take the derivative of the exponent. So the derivative of 2x is 2. And I'm going to times that by my original equation. So that's an x up there. And then all over e to x squared. So we could try to simplify this down, but I do know that I just want to solve this when x is equal to 0. So yes, I could simplify this down. Do I need to? No, because the key is my x is equal to 0. So what I'm going to do is find my y prime at 0 now. I'm just a lot better with numbers than trying to common factor things out, especially when x equals 0. That's a great one to work with. So I'm just going to go along. I'm going to sub in 0 every time I see an x. Oh, me, that just kind of went crazy there. I'll just move this over a bit. Sorry for the messy writing here. Hopefully, though, you're just writing it down yourselves and not trying to copy what I'm doing. Copying down what I'm doing is never the right way. You heard me say I'm subbing in 0 for x. So you should be doing that on your own and then checking my final answer. Okay, so I have in 0 every time we see an x. Now it's about to get a lot easier here. So e to the power of 0 is 1. So we have e to the power of 2 times 0, but anything to the power of 0 is 1, minus 1 plus 0. I'll write that down if you're trying to figure out what I'm doing. And then that was times the 2, and then times e to the power of 2 times 0. So 2 times 0 is 0. E to the power of 0 is 1. All over 1 squared. Okay. Nice and easy here. It's going to turn out really nice. So 1 plus 3 is 4. And then minus 1 plus 0 is 1 times 2 is 2. All over 1, which is equal to 2. So it worked out really, really nice so that my slope is 2. So remember what we're doing here. This is giving me my slope. This is what I wanted to find. I want to find the equation. The derivative is equal to m. So this is y prime, but y prime is my slope. And technically this is y prime at x equals 0. Okay. Now that I have my slope being 2, I need a point for my original equation. So I have the x is 0, but I do need a y value. So I'm just going to, off to the side here, let's figure out just y at 0. So y at 0, again, I'm just going to plug in my original equation now. I'm not doing y prime at 0. I need a point on my function, my original function. So I'm just finding y at 0. It's going to be e to the 0 plus 3 times 0 all over e to the 2 times 0. And I'm going to get that being 1 over 1. So e to the power of 0 is 1, plus 0 is 1. And then the bottom is going to be 2 times 0 in my exponent, which is 0. And I'm going to end up with 1 over 1, or just 1. So the point I have is 0, 1. So that's kind of the important thing I have. Okay, so coming down here, I know I know my slope is 2. I know my x was 0, and I know my y was 1 from everything I found up above. So all I have to do here is very quickly just sub everything in. I don't know why that pen's not working. Oh, I already made a mistake because my technology. Okay, my y is 1. My slope was 2. My x was 0. So I'm very quickly going to get my b is equal to 1. So what is the equation of my tangent of my function at x equals 0? Well, the equation is going to be y equals mx plus b. So there is my formula of my tangent line at x equals 0. So this is going to come back time and time again where we're asked to find the equation of the tangent to a function at a given point. So I just knew x was equal to 0. So I could do this in any order, but because it's calculus, I take the derivative right away. I know I'm going to have to. Then I found my y at 0 after I knew my slope at the given point, and then I found my equation. Okay, so that is Euler's number.